In the last couple of classes, we have been discussing about wave phenomena, or rather the wave propagation across media boundaries. In particular, in the last two classes, we have been discussing largely about propagation across media boundaries, and both media are very good dielectrics. So we have seen different kinds of phenomena when the wave is either vertically polarized or horizontally polarized, and phenomena like total internal reflection and Brewster angle, evanescent fields, so on and so forth. So what essentially happens is that these show you a set of phenomena, some of which you are already aware of, but to say overall, these phenomena present to us a deep insight into the well-known physical phenomena, but from a more rigorous angle. So now let us look at the other obvious type of boundary, that is a dielectric conductor boundary. So again, the assumption pretty much stays the same. This is the z-axis, this is the x-axis, and the xy plane essentially denotes the boundary. So the y-axis essentially starts from here and it's pointing outside. So let this medium 1 be a dielectric and medium 2 be a conductor. So as per boundary conditions, we know that the waves will not lie deep inside the conductor, rather they will mostly exist along the surface, and inside the boundary or inside the conductor body, the waves will either die out very easily, or they will exist in the form of either surface charge or surface current, something of that kind. So in fact, both can also be possible. So let us consider the case of the perpendicular or the vertical polarization. So let's suppose I have a wave which is incident. This is the direction of propagation of the wave. This is theta I. So what we can write, if this is a vertical polarization, then the electric field will be existing along the vertical axis. So let us assume that it is coming out of the plane of the paper. So this is the EI vector. So for the wave to propagate this way, the H vector must exist this way. As you know, this will be HI. Likewise, there will be reflected wave. So by now there is no need to prove that this will also be theta I, and since the electric field has to be continuous, the tangential component, the ER vector will also be vertical to the plane of the paper, and the HR will be along this side. So we can write using direction cosines, we can write the expressions for the incident and reflected electric fields. So I can write EI bar is EI0 bar times e raised to minus j beta 1, or let's call it as beta because there is no concept of beta in the metal. So let's say beta 1 is beta. There is no beta 2 right for a metal. So j beta times this part stays the same as before, x sine theta I plus z cos theta I. Yes. and ER will be ER0 vector times e raised to minus j beta x sine theta I minus z cos theta I. This is what we already know. So what we can say is that let us now go back from this format to writing in the format which shows the direction of the field. So right now you can see that the electric field vector is existing along the y-axis. It is perpendicular to the xz plane, so there are no x or z components of the electric field. So let me write these two equations by separating the unit vector of the axis along which the E field is existing. So that is the way we used to write earlier. So let's do that. So then EI will become, now EI0 will go back to being some scalar quantity. It may be real, it may be imaginary, so that is not a point of concern right now. So this is minus j beta x sine theta I plus z cos theta I. Now we are removing this vector sign from EI0 to denote the axis on which the E field vector exists. So since it exists along the y-axis, the unit vector will also be y cap. So likewise ER I can write as ER0 e raised to minus j beta x sine theta I minus z cos theta I y cap, because this is also along the y direction. So now what? So now along the boundary, that is this line, z will be 0. So what will the EI and ER be? So at the boundary, I can write EI bar is EI0 e raised to minus j beta x sine theta I y cap, and the ER vector will be ER0 e raised to minus j beta x sine theta I and y cap obviously. So what we can say is, at the boundary or at the point of incidence, there are two fields essentially, the incident field and the reflected field. So one is just striking, the other is leaving, the wave rather. But both fields exist perpendicular to the surface. So at the point of incidence where both EI and ER are present at the same space point, so we can say that since these two fields are perpendicular to the surface or perpendicular to the surface of the paper but parallel to the media boundary, this is medium 1, this is medium 2, both of these fields can be considered as tangential fields. So I can say total tangential fields, that is E field, in medium 1, that is nothing but the sum of these two here. The ER0 vector will not be there because the y is written already over here. So the sum of these two fields is the total tangential field in medium 1. Now as per the boundary condition, what will be the field inside medium 2? So medium 2 is a conductor where sigma tends to infinity. So as per boundary conditions, no field can exist inside. So as per the tangential condition for the boundary electric field, this sum will be identically 0. Because there is no tangential electric field which can exist inside medium 2 as a response to tangential field on medium 1 boundary. So looking at this identity will be valid only when the coefficients become equal. That is like saying, or rather the coefficients are equal but with a negative sign. So EI0 will be equal to minus ER0. So this means for this sum to be equal to 0, the two coefficients or the magnitudes, the fields at the boundary, they must be cancelling out each other. So that is what we mean by the tangential component on media 1 being equal to 0. If a wave strikes a metal, an equal and opposite field will be generated, which makes the boundary field as 0. So that's like saying, so if I rewrite this, I can say the reflection coefficient in the vertical polarization case, that is nothing but ER0 by EI0. We had defined this previously already, and that is equal to minus 1. So the gamma at the boundary, the reflection coefficient at the boundary is equal to minus 1. So for transmission line, which load has a load reflection coefficient of minus 1? Simple, it is the short circuit. So a metal dielectric boundary works exactly like a short circuit. So this works like a short circuit load. So this is what happens. Now, it's also very interesting to note that since the medium 2 is metal or a very good conductor, the assumption for short circuit or the equivalency or relating this to a short circuit is not wrong, because essentially a metal has good connection at all points. Between any 2 points, it has a very good connection. So just like a short circuit, you can think of this way also. Now let us take one step ahead. So far we were discussing, let one wave come and do something. It will get reflected, it will get transmitted, refracted, whatever. So in general or in practice, it very rarely happens that a source will give you only one wave. So sources generally give waves which are more than one. You can have point sources which give waves in all 360 directions, 360 degree directions around the source. There are very coherent sources which give you parallel rays of electromagnetic waves. For example, a laser which gives you very coherent rays of light which are mostly parallel to each other. So let us think of it this way, that right now not one but more than one fields are there, or more than one waves are there. So it's like saying, if I have a metallic boundary, so now I'm showing a metallic boundary this way. So just to make it look like as if it's a mirror, this is conductor, medium 2, this is dielectric, medium 1. So if I have an incident wave over here, there will be a reflected wave like this. I can have one more incident wave, I can have one more reflected wave like this. So in general, you will see that in medium 1, there are points where the incident and reflected waves, they briefly cross each other, or kind of they superimpose on each other. So therefore, nothing stops me from superimposing the fields also. So I can say that, let's continue with the case of the vertical polarization. Let's call this as EI. So this will be obviously HI. So the total E field in medium 1, let us call it as the E1, that is the electric field in medium 1. That will be nothing but the addition of the EI vector and the ER vector. So looking at the expressions we have written earlier, it is simply nothing but the addition of these two. So this is nothing but EI0 times e raised to minus j beta x sine theta I plus z cos theta I y cap plus the ER field. But we already have proved that in such case the EI0 and ER0 must be equal. That is the fields at the boundary. So I can say, I can write ER in the same way as the earlier ER, but the coefficient will now be minus EI0. And the rest of it will stay the same, that is e raised to minus j beta x sine theta I minus z cos theta I. I think there was a minus. Yes, there was a minus. So only what has changed is the coefficient of the field. So remember, this EI0 was decided earlier, even when the field had not yet hit the boundary. But the moment the reflected wave is generated, it must be generated with an equal and opposite magnitude. So let's get down to business. I can take some terms common over here. I can say that directly. The y vector will continue to stay outside common. So EI0 and this e raised to minus j beta sine theta I and this beta sine theta I can take outside as common. So I can say EI0 times e raised to minus j beta x sine theta I, and inside what I will get? I will get e raised to this term minus j beta z cos theta I minus e raised to plus j beta z cos theta I. Is this correct? Yes, I think so. So does this look familiar? This is nothing but addition of an even wave and an odd wave, which gives us a sine function. So I can simplify this to E1. I can rewrite as minus 2j, because it is essentially, this 2j will come because of the sign, EI0. The minus will also come because it is e raised to minus j theta minus e raised to j theta. So there is a minus sign which will come. So this will stay, and what I will get is sine of beta z cos theta I times e raised to minus j beta x sine theta I y. This is what we will get. You can quickly correlate. These two terms stay as it is, and this one is becoming that minus 2j sine of this component. So that is what we are getting. Now, likewise, just like for the how we have written for the E field, I can also write the HI and HR vectors for the medium 1 also. So I should say this is E1 bar. Do not forget the vector notation. So I can write HI and HR also in a pretty similar way how we have analyzed earlier for the vertical polarization. So I can say that the HI vector will be if I write it this way, I will get EI0 by eta of the first first dielectric or medium 1 times minus cos theta I x vector plus sin theta I y vector times e raised to minus j beta x sin theta I plus z cos theta I. The x and y, sorry, this will be a z component, I'm sorry. X and z, it has to be z because the electric field is along the y component. So the h has to be on the xz plane. So just keep a sanity check of this, keep track of these components. It's very easy to make a mistake. And HR will now be, since EI0 is equal to minus ER0, I can write this as minus EI0 by eta 1 cos theta I x vector plus sin theta I z vector times e raised to minus j beta x sin theta I plus z cos theta I. So just like how we had found out, because of superimposing multiple sets of incident reflected waves, we have found out the total electric field in the medium 1. We can find out the total electric field, the total magnetic field in medium 1 also, and that is nothing but the vector sum of the HI and HR. So H1, now be very careful, this will be an addition of these two terms, and I will not write them all over again, but what I can do is, when I am adding them up, I can group the x components and the z components together, and then I can say that it will become something of this kind. There will be one x component plus some z component. So let's write down the x component first. So it will be both will have EI0 by eta 1 with a negative sign and cos theta I. So the common term will be minus EI0 by eta 1 cos theta I times this will be a minus sign. Again, take care of this. And the other common term will be the first one, the j beta x sin theta I. So this will be like this times what? The sum of the other two exponentials. So here we have a e raised to plus jz, here we have minus this minus term which is going outside, so this inside will have a plus. So here what we will get is e raised to minus j beta z cos theta I plus e raised to minus j, plus j beta, this minus and this minus will cancel out, z cos theta I. I think that's about it. Yes. Plus again, if I take the z terms common, I can take the minus sign outside and I can write, yes, I think I can do that. Yes, I can take the minus sign outside, and then what I will get is ei0 by eta 1 for the z component. The other thing that will be common is sine theta I. The other thing that will be common is this exponential, just like this one. Now the bracket term will be e raised to j beta z cos theta I minus e raised to minus j beta z cos theta I. Yes. So this will correspond to a cos term and this will correspond to a sine term. So let's write that what it is. Let's write it in the next page. So H1 totally I can write as, there will be some real component and there will be an imaginary component because of the entity. This will give a j sine term and this will give a cos term, but the 2 will be there, which is common. So the first term will simplify to minus 2 ei0 by eta 1 cos theta I cos of beta z cos theta I, and this is the x component. Now I am taking the exponential sine component outside, that is e raised to minus j beta x sine theta I. This I have taken as common. Now the second term will be minus j to ei0 by eta 1 sine theta I. If you look at this, just try to correlate these two. This term I am taking common. This is becoming 2 cos, or 2 times cos of this quantity which we are getting, and that is why the 2 comes over here. In the sine case, we will get 2 sine theta I, and this will be sine of beta z cos theta I, and this will be the z component. So this whole times the e raised to minus j beta x sine theta I. Now we have the total H component in the dielectric. We had derived the E component also. Let us write that down. So the E component is minus 2j ei0 sine beta z cos theta I times, let me just say y cap over here, and this also I will just take outside, e raised to minus j beta x sine theta I. Okay, we have written some very big equations, but let us not be boggled down by them and try to understand what they signify. Let us try to understand what they signify. Now, what I am seeing is, if I were to look at this total electric field, it is of the form of some E10 bar times e raised to minus j beta x sine theta I. And if you look at h1 bar, these two are some vector, but they correspond to some h10 bar times e raised to minus j beta x sine theta I. So now we have brought them back to the way they were looking earlier, or the form which we have been writing earlier. So this becomes equivalent to this becomes equivalent to this. Now again, let us observe some things. Let us observe the nature of E10 and H10. So E10 is a vector obviously, but existing along the y direction. So therefore, this is a vertically polarized field. And the H exists along the x and z axis, which makes the E and H vectors perpendicular to each other or orthogonal to each other. Now, this was the easy part. So you may say, what is the big deal about this? But now, the common thing we see for both fields is that they have this propagation component. That is, the propagation component is there. So now, if I say that, I can say that yes, theta I is a constant. Once the wave is incident, theta I cannot be changed. So therefore, even sine theta will be a constant. So let me say that, let me call this beta sine theta as some beta prime. So now I can say that E1 I can write as E10 bar times e raised to minus j beta prime x, while H1 I can write as H10 vector times e raised to minus j beta prime x. So what do these two indicate? These two indicate the component of a field or the components of a wave, the two field components of a wave that is traveling along which direction? It is traveling along the plus x direction. Now this is something we have not seen before. Why am I saying it's a wave? Because both of them have the same nature, and the nature of EI0 and HI0 is such that they are orthogonal to each other. So therefore there is no need to doubt that there is indeed a wave which is going on that side. So this wave is essentially traveling along the x direction. Now you may say, where is the relationship between the mod of EI by mod of HI0? EI0 by HI0 should be equal to eta. That is not being followed, but it's okay. It's fine. That is the least of my worries, because the major factor that the HI0 and EI0 vectors must be perpendicular to each other, must be orthogonal to each other, they are getting satisfied. What is the ratio that can wait? That is not of my interest at the moment. Whether it's eta, whether it's something else, I really don't care. What I am interested in is that we can see that this causes a wave traveling along the plus x direction. So what we can say? So y is like this. So I'm saying that when I'm making multiple waves incident like this on the boundary, some wave is flowing this side also. And don't mistake it with the field disturbance on the surface. That's a different thing. They look very similar, but that was a field. So I'm not saying that they are not correlated. They are. But this wave is traveling only when the second medium is the metal. It never happens for a dielectric boundary, that we proved, because that e raised to beta x term sort of disappears and we get a stationary wave essentially. So that's how it is. So now this presents us with a very interesting solution. So the question is now, if I make some waves incident from a dielectric onto some conducting boundary, can I make some energy propagate along the boundary? That seems to be something that is doable. So now before we jump the gun, let us take a look at one more thing. Let us take a look at what happens along the z direction. So once we saw that yes, since the waves are incident along the xz plane, the x-axis reaps the benefit of getting some energy being propagated along its path or along its axis. So the question is, does anything happen on the z-axis? So maybe not on this side, but let us say the z-axis on this side of the medium. This is the minus z. So let us look at this. Now what is happening is that we see that the field components of x, z and y, in case of H we have components on the x and z axis. In case of the E, we have the field along the y-axis. The magnitudes of those components, they are all functions of z. You can see that. So I can write, what can I write? I can write that E1 is equal to, just like how I said, E10 times e raised to minus j beta prime x. I can rewrite this E10 as some vector which exists along the y direction, that is some EY0 times y component times this e raised to minus j beta, or let's call it as EY. Let's not write the 0. So this is the way, and H1 is H10 bar e raised to minus j beta prime x. Now this I can write, I know that there is some x component and some z component. So I can write that H1 will be Hx x component plus some Hz z component. Let us not worry about the sign too much at this moment, times e raised to minus j beta prime x. So what we see by looking at this is that Ey, the electric field component magnitude, is some constant times cos of beta z cos theta I. So it is some, let us say, some constant k1 times cos of beta z cos theta I. This is Ey. What about Hx? Oops, sorry, this is sine of, not cos, I'm sorry. Sine. Hx is some constant, let's say k2 times cos of beta z cos theta I. and Hz, what we see is again a sine component with some constant, let's say K3. K3 sine beta z cos theta I. Now what do this indicate? So now suppose I plot the magnitude of each of Ey, Hx and Hz. Suppose I plot this. Let us say I have 3 graphs and this is my minus z axis in each case. Let us say first I will plot the mod of Ey. Now Ey is some k1 times sine of beta z cos theta I. So therefore, if I plot the magnitude of the sine wave, it will be kind of like a full wave rectified signal. So it will be something of this kind. Like this. This is the minus z axis. What about mod of h of z? H of z is also a sine wave times k3. By the way, this will be k1. So this will again look the same. So again it will be the same thing. This will be k3, I believe, yes. And what about mod of h of the x component? That is a cos function. So therefore, the maxima will be along the z equal to 0. So the minima will be here. Something like this. Yeah, something of this kind. So this, let this be some k2 which we had defined. Now what do we see? What do we see? These are standing waves. That's first things first. So the first conclusion we can see is they are all standing waves. Why they are standing waves? Because they are just functions of z. Okay. So you will see that the time function comes over here, whereas the magnitude or the z essentially comes over here, this way. So all of these are standing waves. That is one thing. Now what is happening is that because of this vertical polarization of the E field which exists along the y-axis, essentially this creates fields or standing fields, so to speak, along the z-axis on the side of medium 1. This is medium 1, this is medium 2. So nothing is there on medium 2, they are all tangential fields, or rather Ey is a tangential field, so there is no electric field, so to speak. So what can we say about Hx? So Hz is 0. Hz is the normal component of the magnetic field. It is 0 at this point. Ey is the tangential component of the electric field, which is 0, as we had proved. But what about Hx? Hx is a tangential component. Hx is a tangential component. So as per the boundary condition, the Hx will induce a surface current. The Hx will induce some surface current. So Hx, or the component of the x component of the magnetic field, is a tangential field which is non-zero at the boundary. So it will induce a surface current inside medium 2, which is the conductor. This is the second conclusion I can draw. So now let us talk of power. Let us talk of power transmission. So when we talk of power, we can talk of E and H fields. So let's compare Ey with Hx. So if I have the y component of the electric field and the x component of the magnetic field, as per Poynting's theorem, I can expect some power to flow along the z-axis, either this way or this way. That does not matter. So what is happening is, if you see Ey and Hx, they are 90-degree phase shifted from each other. Ey and Hx, the fields are essentially 90 degrees shifted from each other. So therefore, as per Poynting's theorem, Ey cross Hx will be identically 0 because pi by 2 phase difference. We had proved this earlier. So which means that no power flow along z direction. Plus or minus, that's a different thing that we are not bothered with at the moment. What about Ey and Hz? Ey and Hz fields are in phase. So therefore, they will constitute some power. So Ey and Hz are non-zero. That means as per Poynting's theorem, the power will flow, but along which direction? Along the x direction. So Ey cross Hz is non-zero. That means power will flow along plus minus x direction. And this is exactly what we had proved. That there will be a wave which essentially travels. Let's say it can be along the plus x, minus x. That does not really matter. But we can make it travel. This is very, 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 very important result. So now, since Ey and Hz constitute my power flow, these are the fields on which I will focus. Hx does not constitute power flow. What Hx does is it induces a surface current. That's it. So that surface current will be orthogonal to the boundary as well as the normal to the plane. So it will be either this way or this way. So it will be along the y direction. That's for sure. So that is the surface current which it will induce. So now we can forget about Hx. Hx only generates the surface current. So that's all its job. There is no further deal with Hx. So now focus on Ey and Hz because this is my gold mine. This is my gold mine because these two field components can actually help me transport power along the boundary. So coming back to what Ey and Hz look like. So Ey, we had said it's equal to some k1 sine of beta z cos theta I, and Hz is some k3 sine beta z cos theta I. So what we are seeing is that the nature of Ey and Hz is such that as you move along the z axis away from the boundary, there are the specific values. There are the specific values of z where the fields are essentially becoming zero. So since both of these are sine fields, I can say that Ey and Hz will become 0 when the sine term becomes 0. So that means the argument of the sine, that is same in both cases, which is beta z cos theta I, beta z cos theta I will be some positive or negative integer multiples of pi, where m can be any integer. So then I need not write the plus minus sign, that's okay. So, but nonetheless, what I can write, let us take some positive values of z, or rather positive values of m, and let us see what are the values of z for which we can get this condition satisfied. So z in this case, beta is constant, theta I is constant, so this will be m pi by beta cos theta I. So let me not write it as an integer, let me say m is an element of the set of whole numbers. So m can be 0, 1, 2 like that. But we know that these minimas or zeros exist only along the minus z axis. So therefore, let us take m as positive but with a minus sign. So what we can say, is by looking at this, what are the what correlation can I draw? What is the angle? What is the phase angle between these 2 points? This is some pi, we know that. But the question is, as far as the wavelength of the wave is concerned, or the wavelength of the field components of the wave, so to speak, are concerned, can we make some kind of a generalization? So what we can see is that this distance, generally, since I am writing the mod of the fields, this distance is lambda by 2 from the boundary. So what can I write? So beta is nothing but 2 pi by lambda. So note, this is not beta prime, this is beta. So if I now write this quantity pi by beta, so pi by beta will be what? Pi by beta will be pi by 2 pi by lambda, which is nothing but lambda by 2. So now I can substitute this lambda by 2 over here, which is in place of pi by beta. So I can say minus m lambda by 2 cos theta I. So what do I get? What do I get? This is what I get. So that means if with some kind of a multiple of lambda by 2, is inherently there existing, because cos theta is a constant and what changes is the value of m. So some integral multiples of lambda by 2 is where the Ey and Hz fields essentially become 0. So now this is what is the fact of the matter. Now you may question what is the use of this analysis. There is a lot of analysis of this field. The reason is, what we are seeing is that the field behavior is essentially kind of repetitive after every lambda by 2. So that's quite like saying, the voltage and the current, they sort of the impedance repeats after every lambda by 2 on a transmission line, if you want to use that analogy. So, or even the voltage or current for that matter, they may repeat. So my question is, if you look at this lambda by 2, it has a very special significance. At the boundary, that is z equal to 0, I am having the metallic conductor, where Ey and Hz are 0 and Hx is essentially non-zero. Now if you go lambda by 2, you will see that the exact same thing is happening. The Ey and Hx are becoming 0 and Ey and Hz are becoming 0 and the Hx is reaching a maximum. Exactly the same as what is happening at the z equal to 0. So it's like saying, if I place another conductor along this lambda by 2, I will make absolutely no difference. All I have to ensure is that the wave is hitting either of the conductors at angle theta I. So you may question now, why have I decided to suddenly put another conductor over here? So I leave this class with a bit of a suspense for that reason, and we shall continue in the next class.